Hello everyone. In the first video, we talked about the zero input response. In the second video for this chapter, we talked about the impulse response. In the third video, we covered convolution and its application in finding the zero state response. In this final video, the fourth video, we will cover an example to demonstrate the convolution and the zero state response, and finally the system stability. So let's go to the example. Okay, in this example, we need to find the zero state response for the system described by the impulse response h of t and with input x of t. Now we have the option to rotate either x of t or h of t. So let's carry out the convolution using this integral. So y of t equal the integral from minus infinity to infinity x of t minus tau h of tau d tau. So using this integral, that means I will rotate and shift the input. So h of tau will be just this one, same as above. Now x of t minus tau, let's first plot x of minus tau. So that means I rotate these around the vertical axis, so I get this. Now if I want to find x of t minus tau, then I shift this by the amount of t. If t is negative, I shift it to the left. If t is positive, I shift it to the right. So this will be t, and that edge is minus 4. It will be t minus 4, and this will be 2. So now I found this function, and I found this function. Let's find y of t for all possible value of t. That means for t all the way from negative infinity to t positive infinity. Okay, let's solve the problem in one note. So we're gonna find y of t using this convolution integral. So that means the input will be sliding as t changes value. So let's start for t less than 0. As long as t less than 0, then there will be no overlap between x of t minus tau and h of tau. And this product will give you 0, since there is no overlap, as long as t is less than 0. So then y of t will equal 0. Now what happened if t is larger than 0, but less than 2? In this case, there will be partial overlap. So that will be this one, this will be t, this will be t minus 4. And in this case, the overlap will be only in this region, where x of t minus tau will be 2, and h of tau will be this line. So then y of t for t larger than 0 and less than 2 will be the following. Y of t equal x of t minus tau is just 2, h of tau is just 2 tau d tau. Now here, where is the limit of this integral? Well, the two functions overlap from 0 all the way to t, where t can be anywhere between 0 and 2. So then this lower limit will be 0 here, and the largest it can be t. If you carry out this integral, it will be 4 tau squared over 2 evaluated from 0 to t, and this would be just 2t squared minus 0, 2t squared. Okay, now what happened if t is larger than 2? So let's clean it up and see what happened. It will be much clearer if we do it in Microsoft PowerPoint. So we said in this case here, as long as t between 0 and 2, there is partial overlap. When t is larger than 2, now it's full overlap, and that full overlap will continue until that edge equals 0, until t minus 4 equals 0 or less. There is full overlap. And also this edge here, the t has to be larger than 2. As long as t larger than 2 and t minus 4 is less than 0, there is full overlap. So the condition t minus 4 is less than 0 and t is larger than. From here, t is less than 4 and t is larger than 2. So that means t larger than 2 and less than 4. Okay, so let's calculate y of t for this condition. T is larger than 2 and less than 4. And in this case, the scenario will look something like this. And the overlap will be in this region. So from 2 to t, this doesn't exist. From 0 to t minus 4, this doesn't exist. So the two function only exist in this interval from 0 to 2, and there's full overlap. So then y of t in this case will be from 0 to 2, x of t minus tau is just 2, h of tau is just 2 tau, d tau. And when you integrate, you will get 4 tau squared over 2 from 0 to 2. And this will be 2, 4 minus 0, that's 8. Okay, now what happened if these keep sliding until it reaches somewhere here? And this is t, and this is t minus 4. So as long as this edge, t minus 4, larger than 0 and less than 2, then there will be partial overlap, which is this one. So now our next scenario is t minus 4 is larger than 0. So that means t is larger than 4, and t minus 4 is less than 2. That means t is less than 6. Then we will have this partial overlap. So let's write this condition for t larger than 4 and equal or less than 6. Y of t will equal x of t minus tau is just 2. H of tau is 2 tau. Now the question is, what is the limit again? The limit will be here. This is the overlap. So it is from t minus 4 all the way to 2. The two function overlap and the product will give you a value. So that will be the lower limit is t minus 4 to 2. And when you carry out the integration, again it's 4 tau squared over 2, t minus 4 to 2 equal to 4 minus t minus 4 squared. And you can simplify this and you should get minus 2t squared plus 16t minus 24. Okay, now the question is, what happened if t minus 4 is larger than 2? So t minus 4 is larger than 2. That means t is larger than 6. Well, if t minus 4 is larger than 2, then the input will be somewhere like here. Now there is no overlap anymore. This h of tau exists only in this region, the input exists in this region, and they are not overlapping. These two functions don't overlap, and the product will give you just 0. So then y of t will equal 0. And that's it. So now, as long as t is larger than 6, the output is 0. So let's write the output for all value of t. So y of t equal 0 for t less than 0. For t between 0 and 2, it's 2t squared. For t from 2 to 4, it's 8. For t from 4 to 6, it's this. For t larger than 6 is 0. And that's the final solution. And sometimes when you are done solving the problem, it's good to see if it makes sense. If I try to plot output, let's say this is 4, this is 6, this is t, and this is y of t. So from t less than 0, it is 0, so that's this one. T between 0 and 2, it's 2t squared. It's so it's gonna look something like this. And if I plug for t 2, that will be 4 times 2 is 8. And from t 2 to 4, it's just 8. And from 4 to 6, it's this function. And if you plot it, it's gonna look something like this. And t larger than 6 is just 0 again. So look, this equation here, at this discontinuity t equal 2, it's 8. This at 2, it's 8. Also at 4, it's 8. How about this one, this function? Is it at 4? 8, yes. Go ahead, plug, and you will get 8. Now, at t equals 6, the output is 0. If I plug for t 6 here, am I going to get 0? Yes. And when you see that, that means there's consistency and you didn't make any mistake in integration. Now, the other thing we said, when you do convolution of two functions, the outcome time length will equal the length of this function plus the length of this function. So y of t, the length is 6. Look here, this length is 4. This length is 2. 2 plus 4, 6. Now, sometimes you wonder, why do I have to flip these and rotate it? Because if I take another input, let's say the input looks something like this, then we need to find x of t minus tau, which will be done this way, because the first part of the input, the system will be seeing these parts. This is the last thing that the system will see. So when I do the rotation, x of t minus tau, now this part, which is this one here, when I slide it and multiply by h of tau, let's say h of tau is something like this, when I slide it and multiply, the system here is seeing this part first, and then I slide it further and slide it further and slide it, and as time passes by, the system starts seeing the rest of the input. And that's the purpose of x of t minus tau. Now, we said from mathematical point of view, it doesn't matter if you rotate the input or you rotate h. x1 convolved with x2 is the same as x2 convolved with x1. So if I try to solve this problem by rotating h of tau, I should get the same answer, but the solution would be more difficult. Let's just show you. Rotate h of t, then h of t minus tau will look something like this. And wherever you see t, you replace it by t minus tau. So that would be 2 t minus tau, and this is tau. X of t will be just x of tau. So now I am actually integrating x of tau, h of t minus tau d tau. And if I slide these here, so now I am finding y of t for t larger than 0 and less than 2, because that's where there is partial overlap. And then we will find y of t equal from 0 to t, x of tau is just 2, h of tau is 2 times t minus tau. So that would be just 4t minus 4 tau. Now look here, you're going to be integrating two terms. It's even though it's easy, but then you will carry more integration versus here. You carry out one integral. So it's very important to decide early which one to rotate. Is it x or h? Which one will make the integration easier? All right, let's move on now to the next topic, which is stability. Okay, if I have a system and I need to determine its stability, I have two types of stability: external stability or bounded input, bounded output, or internal stability, asymptotic. External stability, when you don't know exactly what's inside the system, you treat it as a block and you just apply an input, you look at the output. As long as the input is bounded and you get bounded output, then we say externally stable or bounded input, bounded out. If you have h of t that describe the whole block, not as subsystems, then if you integrate the absolute value and you get less than infinity, for example, h of t could be like e minus 4t, 4t larger than 0. Then if I carry out the integral, it will be e minus 4t dt from 0 to infinity, and you integrate that, you will get bounded value. It's not going to go to infinity. Then we say this is externally stable. But if I know the differential equation, or I know the characteristic roots of the system, then I can test it for internal stability, which is more strict. So the first step is you find the characteristic root of the system. So you may find, for example, lambda plus lambda 1, lambda plus lambda 2, and so forth. So you get the characteristic equation and you factor out the characteristic equation and you find the characteristic roots here. Now the characteristic root could be real, like -2, -4, -3.5, or they could be complex, like -3 plus j4. And we said if it's complex, then you will have the conjugate also a characteristic root. Now let's call these sigma and these j omega. And if I plot the characteristic roots on this plane, where this is sigma and this is j omega, let's call this lambda 1 equal this one. So it would be somewhere here, -3, 4, somewhere here. And this will be somewhere here. Now, if all characteristic roots in the left-hand plane, then the system is internally stable. Why is that? Because if I find the characteristic modes, it will be like C1e lambda 1, so that would be -3 plus j4t plus C2e -3 minus j4t. Or if I have another characteristic root here is, let's say, -5, then I will have another characteristic mode, e minus 5t. See, now as t goes to infinity, e minus 3t will eventually go to 0. Same thing here, same thing here. But if you have a characteristic root in the right-hand plane, like here or here, this could be 2 plus j2, and this will be 2 minus j2. Now, in this case, the characteristic mode will be something like this. E sigma, that's 2 plus j2. T, here is constant C1, C2, E2 minus j2, T. See, now this is 2t. As t goes to infinity, this will just go to infinity, the output, and the system eventually will collapse. So if you have a characteristic root, even 1, on the right-hand plane, then the system is not internally stable. That would be this. It's not stable. Now, what happens if you have a characteristic root in the imaginary axis, something like this here? So you may have lambda 1 equal j3 and lambda 2 equal minus j3. Now, h of t will have this form, c1 cosine omega t, where omega now will be 3. Now, h of t will just keep oscillating forever. It will not go to 0. It will not go to infinity. It's just going to be like the function generator you use in the lab. You turn it on. It will keep giving you a sinusoidal wave as long as the system is open. So now we call it marginally stable. But if you have a repeated roots, that means you have another root here and another root here. So you have actually 2 of these. So you have then lambda 3 equal j3, lambda 4 equal minus j3. Now we have a problem, because h of t, it's a repeated root. You will have c1 t cosine omega t, and that t, as it goes up, h of t will grow to infinity. It's just gonna look something like this, and eventually the system will collapse. So if there are repeated roots on the imaginary axis, then the system is not stable. So if you have the characteristic root, you can determine the internal stability. If all of them in the left-hand plane, internally stable. If you have 1 or more in the right-hand plane, and stable. If you have repeated roots on the imaginary axis, and stable. If you have just 1 root in the imaginary axis, then it's marginally stable. So let's look at this example. we have a system and we want to determine its stability. So let's find the characteristic equation. So for this one, it will be lambda plus 1 lambda square plus 4 lambda plus 8 equals 0. And if you factor out these, it will be lambda plus 1 times lambda plus 2 minus j2 times lambda plus 2 plus j2 equals 0. So you have a characteristic root, one at minus 1, another one at minus 2 plus j2, a third one at minus 2 minus j2. And if we plot these here, you have one here, minus 1. You have one at minus 2 plus j2, and one at minus 2 minus j2. So all its characteristic root in the left-hand plane, so this is internally stable. How about this one? Again, you find the characteristic equation and the characteristic root, and you will find lambda 1 equal 1, lambda 2 equal minus 2 plus j2, lambda 3 equal minus 2 minus j2. Now, we don't even have to find this because here we have a problem. There is a characteristic root at 1 in the right-hand plane, and that means this is not stable, internally unstable. So if this is a stable, then it's definitely bounded input, bounded output stable. And if it's not stable here, then we have to find h of t and see if the integral of h of t doesn't go to infinity, then we may say it's bounded input, bounded output stable. But since we have this lambda 1, we know there will be a characteristic mode where C1e lambda 1, which is t, and the integral of these will go to infinity. So that's bounded input, bounded output, and stable. Now for this one, this will be lambda plus 2, lambda square plus 4 equals 0, lambda 1 equal minus 2, lambda 2 equal j2, lambda 3 equal minus j2. Now if we plot these, let's delete these, we have one at minus 2, so that will be here, another one at j2, so that will be here, another one at minus j2. So that will be here. So now we have unrepeated root on the imaginary axis, so that's marginally stable. Now let me give you another one here, D. If I give you this system, now if I find the characteristic root of this system, it will be lambda plus 1, lambda square plus 4 square. And if I factor out these, I will find characteristic root at minus 1, another characteristic root minus j2, another characteristic root at j2, another, because of that square here, another one at minus j2, and a fifth one at plus j2. This is a fifth order system, so you have 5 characteristic root. Now we have a problem because you have a repeated root here. So I have 2 of them, one here and another one here and another one here. And now this is internally unstable. Now since we determined internally unstable, this is also bounded input, bounded output unstable. This is also bounded input, bounded output, unstable. There could be an input that resonates with this cosine omega t and give you a large output. And this also bounded input unstable. This is bounded input, bounded output stable. When we take the Laplace transform, we will see that you may have a system here, E2t, and another subsystem here with h of t. So when you do the convolution of this h1 of t and h2 of t, you may end up with total impulse response that has only negative. So when you look at the impulse response of this big block, there looks like bounded input, bounded output stable. But then when you look internally here, this subsystem is not stable. So there could be input will come here, will cause this subsystem to collapse, and the whole block will be unstable. So just by looking at the external impulse response of the whole system, you can only determine if it's bounded input, bounded output, stable. All right, this ends this video and chapter 2. Thank you for watching, and see you in the next video, which will be on chapter 4, the Laplace transform.